All right, so this is section 5.1, Composite Functions. Composite Functions. It means we're taking pieces of functions and we're making Frankenstein functions. It's pretty awesome. So the first thing that might be confusing is that we have different forms. It kind of changes. We use a different terminology. So let's take a peek at this example problem. Don't write this down. This is just information only. So the first learning objective is form a composite function. So we're putting together a composite function. Suppose that an oil tanker is leaking oil and we want to be able to determine the area, the circular oil patch around the ship. It is determined that the oil is leaking from the tanker in such a way that the radius of the circular oil patch around the ship is increasing at a rate of 3 feet per minute. So our radius increases at a rate of 3 feet per minute. So our radius, r, as a function of time. So now this function notation is starting to become important because it identifies what is changing with respect to what variable. So my r radius as a function of time is 3 times t minutes, or 3t. The area of a circle is pi times your radius squared. So the area as a function of radius is pi times radius squared. Now what if I wanted area as a function of time? So I can predict if this oil tanker is allowed to leak for the next 20 minutes before my cleanup crew arrives, how big is my oil spill going to be? Area as a function of time, we are going to take out the r and put in the 3t. So then my area as a function of time is going to be 9 pi t squared. And that's called a composite function, when we put together two separate functions to get a new function. Okay. This you do have to write down. When you're given two functions f and g, the composite function is f composed with g. So it has a little circle, kind of like a degree mark. And I usually will read this as f of g is defined by f of g of x. You can also write it as the f parenthesis g of x. Note that none of these symbols indicates multiplication, but it just tells you you are plugging in the g function into your f function. So you're combining two functions. The domain is the set of all numbers x in the domain of g, such that g of x is in the domain of f. So when they're asking you domain, you first have to look at the domain of g, see if there are any restrictions, and if there are, how does that affect when you put g into the function f. So I wouldn't bother with domain. I would take it case by case, look at what your functions are telling you, then establish the domain and range like we have been doing. So here's a little diagram. If it doesn't make sense to you, it's totally okay. Because it's supposed to be a help, and if something doesn't help you, it's okay to not. Okay, so if here I have the domain of G, and there's a certain restriction when I plug in f of G, when I plug in G to my f. Whenever I restrict my domain 4 will restrict the yeah, I'm just going to skip this diagram. Sorry, guys. It'll make more sense with the example problems. Okay, so this is where I want you guys to start writing. For sure, write this down. We have a function f of x equals 2x squared plus 3. G of x is 4x cubed plus 1. We're going to find f of g of 1. We're going to find g of f of 1. We're going to find, this might be crazy, we're going to plug our function f into our function f and let x equal -2. And we're going to plug our function g into our function g and let x is equal to -1. In this case, the way we format is more confusing than the actual math. So f of g of 1 is the same as plugging in 1 into my g function, getting that value, and plugging that value into f. So g of 1 is 1 cubed times 4, which is 4, plus 1, which is 5. So I'm going to take that 5, plug it into my f function. So f of 5 is 2 times 5 squared plus 3. 5 squared is 25, times 2 is 50, and plus 3 is 53. So let's look at b. b is g of f of 1. So I'm going to take my f function, plug in a 1. F of 1 is 1 squared times 2 plus 3. That is 2 plus 3, which is 5. Then I'm going to take that 5 and plug it into my g function. So g of 5 is 5 to the 3rd power, which is 125, times 4, which is 500, plus 1, which is 501. So all we're doing is we're plugging, I like these ones where we plug the number in first and find the value. It's a lot more straightforward. Our third one, we're going to take our f function, plug in -2 and find the value, and then plug that value back into the f function. So if I take -2 and I square it, I get 4, times 2 is 8, plus 3 is 11. I'm going to take that 11 and I'm going to plug it back into my f function. So I'm going to square it. 11 squared. It's 121 times 2 is 242. And then plus 3 is 245. All right, so let's take a moment. Try D by yourself. So we're all going to take a moment. We're going to try D and see what you guys get for your answer.
I did. I just saw it wrong on the calculator. I got the right answer.
Okay. So when I put -1 into my g function, we get -1 to the 3rd power, which is -1, times 4 is -4, plus 1 is -3. So I take that -3 and I put it back into my g function. So I get -3 to the 3rd power is -27, times 4 is -108, and then plus 1 is -107. You can use your graphing calculator to do composite functions. I don't particularly find this. I have never used my graphing calculator to use a composite function. I tend to just do it on my own, but you guys are more than welcome. If you put in one function into y1 and one function into y2, and then set up your parentheses as such, it will you can do composite functions on your calculator. All right, finding the domain of a composite function. So if I have f of x equals 2x squared minus x plus 4 and g of x equals 4x plus 1, we're going to find the composite function f of g, and we're going to find g of x, and then find the domain of each of those. So I'm going to take where my x is in f of x. So right next to the 2 squared and right after the minus sign, I'm going to put parentheses where that x is and shove in my entire g of x function. Replace it with 4x plus 1. So anywhere there's an x in my f of x function, there is now going to be a 4x plus 1. So you put parentheses where your x goes, you shove your entire function into there, kind of like stuffing a turkey on Thanksgiving. You just shove it all in there and let it cook. Then you simplify your terms. That negative distributes out to the 4x and to the 1, and then 4x plus 1 foils out to 16x squared plus 8x plus 1, and then the 2 foils on out. I'm using FOIL in the completely wrong method, so apologies. And then we combine like terms. Actually, the 2 distributes out. Thank you very much. So we distribute the 2, and then we combine like terms. And in this case, it's 16x minus 4x and 2 plus 3 gives us 32x squared plus 12x plus 5 is our composite function. Now, is there any restrictions on the domain for that function? Give me a yes or a no. Any restrictions on the domain? Any square roots? Any fractions? So there are no restrictions on this domain. So the domain is a set of all real numbers. All right, let's repeat this process, but instead of f of x, we're going to take where the x is in g of x. We're going to put parentheses right after the 4, and we're going to shove the entire f of x function into there. So if f of x is 2x squared minus x plus 4, we're going to take the g of x function where the x was next to the 4, we're going to put parentheses, and we are going to make it 2x squared minus x plus 4. Then we're going to distribute that 4 out and combine like terms. So that means the 16 and the 1 combine together to give us 17, and that's 8x squared minus 4x plus 17. And since there are no square roots, there are no rational denominators, the domain is a set of all real numbers. So I find it more helpful to look at the domain after I put the composite together than to try to noodle it before. Keeping life simple. I'm going to read this because the book feels like it's important enough to make a whole entire slide out of it, but just stick to logic. G of x must be defined, so any x not in the domain of G must be excluded. F of G of x must be defined so that any x for which G of x is not in the domain of F must be excluded. So here's where we get to the nitty-gritty. Now we got some polynomials in the denominator. So if we look at the g function, we cannot have x equal to negative 1. Not allowed, because when that happens, g of x has a 0. So we're finding the domain of g of x first. So we have to exclude the -1 from the domain of our composite function. Makes sense. If it doesn't go into g of x, it doesn't go into f of g of x. All right. The domain of f is x not equal to 5, because when we plug 5 in, you get 0 on the denominator of f. So if we put g of x in this function, g of x cannot equal 5. So if we find where g of x is equal to 5, we have 2 over x plus 1 equals 5. Because if our g of x function equals 5, it'll cause our f of x function to have 0 in its denominator. So if I multiply both sides by x plus 1, distribute out the 5, minus 5 from both sides, and divide by 5, I get x equals -3/5. So my domain is a set of all real numbers except -1 and -3/5. Okay, let's take a look at those functions again. We're actually going to find f of g, so we're going to take out in remembering our domain, we're going to take out x in our f function and replace it with 2 over x plus 1. So where we see the x in our f function, we are going to replace it with 2 over x plus 1. So instead of f of x, we have f of 2 over x plus 1. Then we got to do some simplifying algebra skills. We multiply everything by x plus 1, and we get 3 times x plus 1 and 2 minus 5 times x plus 1. We distribute out the -5 and get negative and distribute out the 3. So we get 3x plus 3 on the top, 2 minus 5x minus 5 on the bottom. We combine 2 minus 5, and we get -5x minus 3. And then we factor out this minus, so we get -3x plus 3 over 5x plus 3. So domain-wise, we cannot equal -1, because that makes g equal 0. And we cannot equal -3/5, because that would make f of x equals 0 when g of x is 0. So one more. f of x. So we're going to take, this may sound crazy, we're going to take our f function, take out the x, put parentheses, and put a whole nother f function inside those parentheses. So where this x is here, I'm going to take it out. I'm going to put a 3 over x minus 5 right here. Then I'm going to follow the same process as before. I'm going to multiply the top and bottom by x minus 5. Simplify, simplify, simplify. And get 3x minus 15 over -5x plus 28. So my domain now, because I'm just dealing with f functions, my domain is anywhere f of x is, the denominator is equal to 0. So I cannot have my denominator, I can't have x equals 5. And then I also can't have the denominator of my composite function equal to 0 either. So -5x plus 28 is equal to 0 at x equals 28/5. So I subtract the 28 and I divide by 5. Okay, so if I have f of x equals negative 2x plus 1, g of x is negative 1/2 x minus 1, we're going to show that f of g of x and g of f of x are equal to x for all x values in our domain of the two functions. So the first thing we do is find f of g of x. So we're going to take our f function, we're going to take out this x and replace it with g of x. So when we do that, we get negative 2 times negative 1/2 x minus 1, quantity plus 1. We simplify that down to get x minus 1 plus 1, which is equal to just x. So the next thing I'm going to do is I'm going to find g of f of x. So I'm going to take my g function, where the x happens, I'm going to take it out, and I'm going to shove in negative 2x plus 1. I'm going to distribute. Actually, I'm going to simplify this. 1 minus 1 is 0. Negative 1/2 times negative 2x. Negative and negative give you a positive. 1/2 times 2 will give you x. And that's it for today's recording.